It's pretty wild when you stop and think about it. How do we take a hunk of metal and silicon, it's basically a super fancy rock, right? And get it to do, well, everything. From streaming your favorite shows to guiding spaceships. It all boils down to one simple idea: communication. So, let's get into it. Let's talk about the amazing story of how we actually taught these rocks to think.
So here's the fundamental puzzle, right? At its very core, a computer is just a massive collection of billions and billions of tiny switches. They can be either on or off, a 1 or a 0. That's it. So how in the world do we take a complex idea, something like, hey, play my favorite song, and translate it into a language that's simple? That's the big question, and that's exactly what we're going to break down today.
All right, so first things first, let's get to know the machine we're actually trying to talk to. What is this thing really?
Okay, so the most important part is right there in the middle, a stored set of instructions. See, a computer is incredibly fast and it's super powerful for sure. But here's the thing, it isn't smart like you and I are. It's really just an amazing instruction-following machine. It's just sitting there waiting for us to tell it exactly what to do with whatever data we hand it.
And if you peek inside any computer, you'll find a bunch of specialized parts. You can kind of think of it as a little team. There's the brain, the CPU that does the thinking. You've got the memory, which is like its short-term scratch pad. And you've got the unit that does all the math and logic. But here's the kicker. All these parts, they're just sitting there, totally dormant, until we give them the instructions. They're waiting for the playbook.
Okay, so if the computer is like this super fast chef waiting in the kitchen, then our job is to write the recipe. And I mean, this recipe has to be flawless. Absolutely perfect.
And really, that's all a program is. It's just a very, very detailed recipe. It's a sequence, a step-by-step guide that tells the computer how to get from point A, the problem, all the way to the finished dish, the solution.
And this right here, this really shows you the huge difference between how our brains work and how a computer thinks. If I say, draw a square to you, you know what a square is. A computer? Nope. It needs that idea broken down into the most ridiculously basic, literal steps you can imagine. There is zero room for interpretation. Absolutely no guessing allowed.
Yeah, that precision is absolutely everything. Think about it with the recipe analogy. If you're baking a cake and you totally forget the sugar, or maybe you add it at the very end, you don't get a cake, right? You get, a weird savory biscuit. With programming, it's the exact same deal. The order of the steps and making sure every single one is there. It's the whole ballgame.
Okay, so we've hit a bit of a snag. We know we need to write this super detailed recipe, but we can't just write it in plain English. The computer has no idea what mix the flour and sugar means. So we've got a classic translation problem on our hands.
So the way we solve this is with what you can think of as a language ladder. Way up at the top, we have what are called high-level languages, things like C++ or Java. They're designed to be much more human-friendly, kind of structured like English, so we can focus on the logic of our recipe. Then, as we go down the ladder, special programs called compilers act like expert translators. They take our human-friendly recipe and convert it step by step into languages that get closer and closer to what the machine actually gets, which, at the very bottom, is just those ones and zeros.
And honestly, why does this even matter? Because trying to write a program directly in ones and zeros would be basically impossible for a person. It's just not how our brains work. So these high-level languages, they're one of the most brilliant inventions in all of computing. They let us, the humans, focus on the what, the actual logic of the recipe. Instead of getting totally bogged down in the how, the nitty-gritty details of flipping billions of tiny electronic switches. All right, so now it gets even more interesting. Even once you've picked a language to write in, there are still different ways to actually approach writing your recipe. Think of them like different philosophies or different styles for organizing your instructions.
Yeah, in the programming world, these are called paradigms. They're basically different schools of thought. For example, the imperative style is your classic, straight-down-the-line list of commands, just like a normal recipe in a cookbook. Do this, then do this, then do that. But then you have something like the object-oriented style, which is totally different. It's more like creating a team of little mini robots, where each robot has its own special skills, and your job is to tell them how to work together. At the end of the day, they're all just different strategies for getting to the same place. A clear, working program.
All right, time to put all the pieces together. Let's take a really simple human idea and actually walk it through the whole process, turning it into a set of instructions a computer could actually follow. So the problem is this: add 3 numbers. That's it. Super simple, right?
We want the computer to take any 3 numbers we give it and spit out the total. A piece of cake for us, but how do we turn that into a recipe for our machine?
Okay, first up, we have to break down the logic. Pretty much every program you'll ever see has this basic structure. You've got your inputs, think of these as the ingredients. You've got the processing, that's what you do with the ingredients. And finally, you have the output, which is the finished dish you serve up.
Now we take that logic and we turn it into a super precise step-by-step sequence. What you're seeing here is called pseudocode. It's not a real programming language, but it's like a blueprint that's structured like one. And just look at how every single little action is spelled out. Step 1, read the first number. Step 2, read the second. Step 3, you get the idea. Then you do the math, and importantly, you store the result. And the final step, print that total. See, there is absolutely no way to misinterpret. And that's it. That's the whole journey in a nutshell. We started with a simple human goal, we broke it down into its logical parts: input, processing, output. And then we wrote a crystal clear step-by-step recipe. Now from here, a programmer would take this pseudocode and translate it into a high-level language like C++, and then the compiler and the computer would handle the rest.
So you see, programming isn't some kind of dark magic. It's really the art of creating perfect, crystal clear recipes. It's all about translating our human way of thinking into a logical form that a machine can execute without a single mistake. So that brings me to my final question for you. Now that you know the basics, what recipe would you write for a computer? What problem out there are you ready to solve?